So with that, thank you very much for being here. Thank you, Grant, for introduction. So the topic of what I will be presenting is top-down modeling. It's the data-driven, purely data-driven reservoir simulation and modeling using AI and machine learning. And I am part of West Virginia LEADS, which stands for Laboratory for Engineering Application of Data Science, given the fact that there is a big difference between the engineering application of AI and machine learning versus non-engineering application, and that's something probably that should be discussed. But without any start, let me give you an outline. So I'm going to start with giving you a definition of TDM in a nutshell, one simple definition, and then I will start by giving you a summary of the capabilities of this technology and also its actual validation, not an academic validation, but the validation in the real world use cases, several, the forecast and optimization. I decided to do that first before going into the details of its development, because if a technology is not capable of doing certain things, or at least claim it has this capabilities, but then claims is one thing, but you have to actually do it and validate it, and by that I mean actually blind validation, forecasting the future. And because once these two are there, then if people are interested, then they would be interested to see what this technology is. Because if there is no validation of a technology or what its capabilities are, then it really doesn't matter how it's developed. Whether you share it or not, it's a completely different story. It doesn't really matter. But the key is the technology should be something that its capabilities are of interest to scientists and operating companies and the service companies in oil and gas industry. And then it has to be validated, the claims that are made. So after that, then I'm going to go and talk about the details of how it's developed. The key behind everything in top-down modeling is spatial temporal database. Literally, this is, and that's what I'm now calling it, the spatial temporal learning, because it's very different from all other application of AI and machine learning. And of course, then at the end, I'm going to show you one of the recent use cases that we have done for one of the operating companies. And again, none of these things that I'm presenting here is academic. All of them is applied in real world to operating company all over the world, and I show them to you who they are. So with that, let's start with giving you the reservoir analytics, and I tell you why I call it reservoir analytics, because it's applied both as a top-down modeling and as a smart proxy, and I'm going to give you that definition. But this technology, actually, its contribution is to reservoir management. And reservoir management needs tools that are accurate and has high speed, because the managers like to perform these analyses hundreds and thousands of times before make a decision. And the decision they make has to do with field development planning, uncertainty quantification, and production optimization. And what we have to work with in the industry, we have field measurements. These are the facts, these are the real stuff that we have actually measured. Things such as seismic survey, well construction, trajectory detail, well logs, core analysis, well test completion and workover, hydraulic fracturing, operational constraints, injection and production history. This is what we all get started with. But traditionally what we do is we build, or we ask the geoscientists and petrophysicists and geologists to build a geological model for us. And then we'll take that geological model and we upscale it, or they upscale it for us, and we build a numerical reservoir simulation. Then we take that numerical reservoir simulation and try to do reservoir management with it. But the fact is, if you have dealt with the operating company, you know that especially the big ones, which have teams of reservoir modeling and teams of reservoir management, these two teams, these two groups do not necessarily speak in the same language. They don't necessarily very much like each other. one of the main reasons that reservoir managements are very critical of reservoir simulation and modeling is because the use of numerical reservoir simulation in reality, not in the academia or research, but in the operating companies, in the reality in the world, that's pretty impractical, because in order to make a decision, you have to run the model a very large number of times, do uncertainty quantification, and find out what is the optimization. And doing that using numerical reservoir simulation is really impractical. That's a real numerical reservoir simulation situation, which for a real field, it usually has tens of millions of grid blocks, and even if they use HPCs to do that, they cannot run it that many times. So anyways, with that said, TDM, or top-down modeling, which I'm going to cover here, goes directly from field measurements without any other step, and uses that in order to provide a tool for reservoir management. Of course, the same technology can be used to develop smart proxy models. The difference is that instead of the data coming from the field measurements for smart proxy modeling, the data can come from numerical reservoir simulator. That you can run the model about 10 to 20 times, generate the data, use that data in order to build your smart proxy, and then your smart proxy actually can be run on a tablet and you can run it millions of times. And of course, it is possible to use the geological model directly to build the TDM. We have done that before. One of the operating companies requested for us to do that. We were able to do that. And instead of going through a numerical simulation, you can use the geological model to build a smart proxy without any upscaling. That is also possible. So these two technologies, which is TDM or SPM, are the petroleum data analytics, and that's in a nutshell what this technology is. So to give you one more, a little more definition of that, TDM is a reservoir management tool. It has very small computational footprint. It can be run on a laptop, or very soon, hopefully, it can be run on your smartphone. It's a tool that is used for field development, including uncertainty quantification, and it uses field measurement directly to build and history match a top-down model and use it in order to perform all the things that I'm going to talk about today. So what are the unique characteristics of the TDM? The most important one is, unlike numerical reservoir simulation, which is a reservoir model, TDM is a coupled reservoir and wellbore model. And for those of you who have been involved in using numerical reservoir simulation in a real case situation, I think somebody that is on the phone needs to mute their phone, because we're hearing that. Anyway, so the input to the top-down model is choke setting and or wellhead pressure, or wellhead temperature, or flow line pressure. That is unlike numerical reservoir simulation, that the input, or what they use in terms of pressure, is flowing bottom hole pressure, something that's hardly ever measured in real world. And oil production in TDM is the main output of the system. And the reason I say that is because for those of you who have been involved in numerical reservoir simulation, not in the academia and research, but in real world situation, you know that oil production during the history matching is an input to the numerical reservoir simulation. It is not an output. The output actually is flowing bottom hole pressure, because that is something that they do not have the option to measure it all the time. Other outputs of the TDM are oil, gas, water production, reservoir pressure, and water saturation, and those are simultaneous all at the same time. The next key issue about TDM is its history matching process is completely automated. There is very little involvement of the user. The history matching top-down model makes absolutely no assumption. It makes no interpretation, and it makes regarding geological characteristics that is measured. In other words, all the measured values, data, which is mainly to a very large extent seismic and logs and core, they are honored 100%. And of course, you can do uncertainty quantification afterwards. Some of the questions that are usually asked, one of them is when I present this, they say, but the data that we use is uncertain and noisy. How can we use that data in order to build a model? Well, the first thing is the same is true about any other type of modeling that you make. Numerical reservoir simulation or RTA, you use the same data, don't you? Okay, so, but the fact is, when you use the data from the real world, and nature is always uncertain and it's always noisy. That's a fact. But keep one thing in mind, that human brain processes real data all the time. And one of the most important characteristics of AI and machine learning is the fact that it's capable of handling uncertain and noisy data. Please don't get me wrong, I'm not talking about outliers and some of the data that are quite wrong. We have to handle that. But in terms of noisy data and not necessarily 100% certain data, that is something that AI is capable of doing. Why? Because human brain does that all the time, and AI and machine learning are tools that mimic the way human brain deals with the data. That said, the next one is, how do we know we have enough data to build a top-down model? Well, in a short, simple sentence, I can say if you have 30 wells and about 3 years of production, then you have enough data to get TDM started. Comparing numerical reservoir simulation models, how hard and time-consuming is the history matching of top-down modeling? As I mentioned, it's literally incomparable because it is completely automated, the history matching, and it can be done very, very quickly. In numerical reservoir simulation, you can do modification, which is global-based, to history matching, and 99% of the time that doesn't work. It may enhance the model a bit, but it cannot history match hundreds of wells that you have. Then you have the next step is regional modification, reservoir compartmentalization and modification. That again takes you further closer, but 90% of the time that doesn't work. And we all know that the numerical reservoir simulation, in order to get a history match, you have to go and do local and well-based modification, transmissibility changes and skin changes around each single wellbore in order to accomplish the numerical history match. That does not apply to TDM. To TDM, the only thing you modify is a global modification, which is the whole thing. Everything that I'm talking about here in this presentation in detail is presented in this book. This book was published by SPE, and all the details of how to develop data-driven reservoir modeling can be found in this book. With that, let me talk about what are the capabilities of TDM. First of all, let me share with you that TDM has been applied to so many different fields all over the world, from U.S. to Central America to Europe, North Sea, a lot in Middle East, and then in Southeast Asia. So everything that I'm presenting here to you is not theoretical, it's actually based on actual situation. So one of the first things is the results that you see here in history matching. One of the first things we do, we take the entire time and we divide it in two general pieces. The first piece we use to do history match, and then we put away a part of that data, and we call it blind history matching. We built a history match model from beginning to right here, let's say, and then we deploy it and we forecast, TDM forecasts the rest of the time, and then we have the results actually, and you can compare it. This is been done. This is a field in an onshore field in Middle East, and these are two examples of two wells that have been history matched and blind history matched for oil production, reservoir pressure, and water saturation, and then this is the forecast part of it. And we call it validation in space and time. This is the validation in time, as you can see. But this is two more wells that were drilled after the time we used to history match. Therefore, that is not only validation in time, but also validation in space. These are two separate new wells. Another thing that you can do in real time, actually, on a laptop, you can perform single parameter sensitivity analysis. You can change, for example, here you're changing the choke setting from 5 to 125, and just by click one button, you can see how oil, water, and gas production is impacted during the history and during the forecast for these different sensitivity of the model to these different choke settings. Sometimes you want to do multi-parameter combinatorial sensitivity analysis. In this case, another well in the same field, we simultaneously did sensitivity analysis for 4 different parameters: completion, pay thickness, permeability, and porosity. Given the fact that it is a multi-parameter combinatorial sensitivity analysis, you have to do you have to perform this analysis literally tens of thousands of times. That cannot be done in real time, but it only takes a couple of hours to do that, and it gives you a range of oil, gas, and water production that goes in. You can actually optimize water injection. This is a field that we did again for the Middle East. From 1975 to 2014 that we did this project for this company, we looked at their historical data, and we identified that if they would have inject 15% less water that they actually did, they would produce 2% more oil. That 2% in that field, that's about 10 million barrels, so very, very large. And I give you examples of this as we move forward in this presentation. And another thing that we can do very easily with this technology is map the reservoir conductivity. That goes beyond just permeability mapping. It is when you talk about reservoir conductivity, specifically when you have CO2 or natural gas or water injecting in order to enhance oil production, then you are combining thickness of the formation, the permeability of the formation associated with mobility of the fluid, which has to do with its viscosity and its impact of pressure to it. As we move forward, what you can do, you can actually once you build the model, you can literally run it tens of thousands of times, even millions of times, in order to identify, for example, in this particular field in the Middle East, again, the ones in the middle, these are all producers, these are all injectors in a periphery. And what we were able to do, we run the model tens of thousands of times and identify which injection well is contributing to incremental production of oil, and then identify which one is the highest contributor and which ones are the lowest contributor. The next item is, and that's the same thing that I just showed you that we did. You can identify how injection of water, or in the case that we are working with in this project, is CO2, how much CO2 you should inject in order to increase production, if that's the objective of CO2 injection. I'm going to go to the detail of this one in a little bit. This is, then you can add economic to it and identify net present value of different WAG systems where you have water and gas, or water and CO2 injection, whether you have 3 months each, 3 months gas, 6 months water, 3 months WAG, or 3 months each again, but the volume changes and so forth. And you can see the history match has been done, and this is the oil production forecasting, and allows you to perform net present value economic calculation. Another thing that you're able to do with this is choke setting optimization, because you cannot optimize flowing bottom hole pressure in realistic fashion because you don't have any tools to measure flowing bottom hole pressure. And there's a difference between the flowing bottom hole pressure and choke setting and wellhead pressure, unless you put an equation there and you can change it the way you want. But here is an example that tells you that the original production of this particular well, as you can see here, and the optimized is this. That's the difference that you did. As you can see, GOR and water cut does not changes. And here, what you can see is the line in the red is actually what you identified, how to optimize, change the choke setting in order to optimize production. And you can see this is GOR, and this is water cut, and this is the level that they don't have to pass, otherwise you cannot open the choke to a certain amount. And another thing that can come out of it is actually one of the things that separates this technology from our traditional numerical reservoir simulation is that geology a lot of time becomes an output rather than an input, because when you talk about geology, there's a lot of interpretation associated with it. And since this technology stays away from interpretation, so the output can be the geology can be an output. This is an example that we did in this particular field. Historically, they injected. If you would have injected all of the historical, you could see what happened to the oil saturation. Where if you had less injection, how would that impact the saturation? And I show you how that actually impacted. I mentioned that you had to. In this particular case, you had to inject 15% less in order to increase production a bit, and I will show that in a few wells in a minute to you. What are the limitations of TDM? It's only applicable to mature field. You cannot apply that to. You cannot apply it to green fields. So you have to have field measurement in order for this to work. If you have green field, you have to use a smart proxy model. That's still an AI technology, but it is not the TDM. So you should have at least 3 years of historical production. It is not valid once the physics of the fluid flow in the field changes. In other words, for example, let's say you have the data only from primary production, and now you want to see what happens if you inject certain things. Well, that changes the physics. Since you don't have the data for that, it doesn't work for that. You can build the model for primary and then update it as you inject after 6 months, let's say, or depending how many wells you have, and then you can move on and use this technology. So let me show you some of the validation again, because if there's, as you probably say, it's a lot of claim is being made. The key is, are these claims, can it be in the real world situation, be tested to see if it works? This is an example I'm giving you, and I can actually show you the field. It's called Buhasa in United Arab Emirates, ADNOC. They allowed us to share that, so I can share it. I can tell you exactly what it is. What they wanted to do 5 years after we built the model, they called us back in, and they said, we're going to give you 23 new locations for the wells that we drilled in the past 5 years since the last time you performed this model for us. And the question they asked us was, if we give you the location, can you tell us when we drilled these wells, what was the pressure and what was the water saturation that your model tells us we would get at those locations? And so it's, again, in the 5 years that the model has not been updated. And this is the result that they actually shared with us. So they gave us those 5 different formations. The wells were drilled into, and this is the combination of these 23 wells. And when you look at it, and they gave us the location, we gave them the pressure, and they gave us the results. The results shows that about 35% of all the TDM predictions were more than 95% accurate. The next 26% were between 95 to 90% accurate. Another 30% were 90 to 80% accurate, and 8% or 9% were between. So there was nothing less than 70%. So more than 90% of all the TDM predictions were more than 80% accurate on these 23 wells that we did for this particular. And then we also did it for water saturation. And this is the distribution of accuracy of our model. Again, this was 5 years without being updated. And this is 70% of the TDM predictions were more than 80% accurate. This is another one that I cannot tell you exactly where it is. This is in Caspian Sea. This is much, actually only 2 years ago we did this. And we did choke setting optimization after building the TDM. And then they compared our prediction and they actually used it in the field. And they shared the detail with us. And I'm here telling you the detail they had. They had two sets of, it's the offshore. So they had two sets of wellhead, low pressure wellhead and high pressure wellhead. 19 of their wells were flowing in the low pressure, the rest were flowing in the high pressure. And they asked us if, they gave us 3 wells, and they asked us how could we change these 3 wells. They were originally clicked in the high pressure. They asked us should they be, should they do? They actually gave us a lot more than that. And we told them these 3 should be switched to the low pressure. And they did that, and this was incremental oil production on a per day basis for these 3 particular wells, and which is about, that goes to about $5 million on an annual basis. So the change of the wellhead system did not negatively impact the GOR, gas oil ratio, water cut, or reservoir pressure to go below the bubble points for the gas to come out. So that was the key about these predictions. How you get, which wells you open the choke to what percent in order to make sure that that you still produce more oil without changing the water cut. And this is, then we had identified 4 places for them to drill new wells. And this is the email that they sent to us. I'm not showing you all the details, but it tells you that we would like to inform you that the results of prediction scenario of this particular field indicated a good location for this particular well, and it has been proven with completed new. That so they drilled it, and the result that they gave them, at least for these 2, they have done it, and they came up to the conclusion that it works correctly. Then they gave us 15 wells, and they asked us to give them optimization. If they were in low pressure or in high pressure, they wanted them to tell you whether they should switch it or keep it. And these are the 15 that we asked them to switch from high to low or from low to high in order to change production, optimize the production. And based on what they have mentioned here, the result of 13 out of 15 were correct. So 87% of the TDM choke setting optimization that was recommended after they tested came out to be correct. And this is the same field that we forecasted in the background, and then as you can see, this is the TDM forecast, and this is what they were produced, and they shared it with us, and you can see how good was the TDM's forecast in terms of future. The only input was the choke setting that we got from them. So that provides you with enough. So let me talk a little bit about how do you go and in detail and develop the TDM. Again, in that book, all the detail is provided. We start with only field measurement, static data and dynamic data, from well trajectory survey to seismic and PBT and log. And the dynamic data, operational constraint plays a very important role, all the injection and production data. We build what we call spatial temporal database. I'm going to explain it in a minute to you. And then we use that spatial temporal database. We build a very general static model without making any interpretation. We use fuzzy pattern recognition in order to identify which parameters, what kind of impact they have. And then we do all of that, and this is how we build the TDM, the top-down modeling. It's a combination of multiple neural networks that are sequencing each other and feeding each other one as we move forward. This is, for example, this particular one has 5 different models that cascading one another. So once you do that, you have to validate it in time and space, as I mentioned earlier. If the validation doesn't work, then you need to go back to spatial temporal database and figure out what was it that you didn't do correctly in order for that to happen. If it actually works well, then you can use it and run it literally millions of times in order to do production forecasting, sensitivity analysis, optimize infill location for producer or injector, and so forth. I'm sure in other presentations that you were exposed to, the machine learning algorithm, the neural network is presented to you. It's really not that complex, so if the mathematics behind neural network is something you're interested in, it probably, as engineers, it's going to probably take you a couple of hours to figure it out, because the mathematics behind overwhelming number of machine learning algorithms, the mathematics behind it are very, very simple. Especially when you compare it to some of the engineering detail that you have to deal with it when you are building the physics-based model. So this is a simple neuron. The inputs go and you have a summation, which is a dot product of the two vectors, and then it goes to an activation function, and then you come up, and this is the simple mathematics that provides you with the output, and then what you have to do once you get the output, that's for a single neuron. In a complete neural network has a large number of neurons that goes, inputs that goes to multiple neurons in multiple hidden layers, depending on how you develop it. These are really, to be honest, they're not that important, because why? Because the mathematics behind it is so simple. Furthermore, you can actually download open source of these algorithms so easily. So in a way, you shouldn't waste your time to become an expert in the mathematics of AI and machine learning. Even if you want to become, it's going to take you a very, very short period of time to do that. But and of course, once you have the output of the neural network, then you compare it in a supervised learning. You compare it with the actual output that you have, and then you use gradient descent or backpropagation or other algorithm, which essentially what you're trying to do is to identify how to minimize the error through the gradient descent process. And again, I'm not going to give you much, to be honest with you, I don't want to waste your time on the mathematics behind it, because I'm sure you all know it, and if you don't, it's going to take you very little to figure it out. For here now, when it comes to top-down modeling, it is all about how you use the data. And here I have the data that we use in order to build the numerical, the top-down model, from well data to completion data to reservoir data. And if you look at it, all of them are measured data, none of them are interpreted data. And if available, all of this data, we use artificial lift is important. Every piece of information that you have is important. And these are the other things that if it is available to you. And again, another nice thing about TDM is there are not certain parameters that if you do not have, of course, I'm not talking about the output or what you're trying to history match, but for example, if gamma ray is not available or permeability is not available, you do not fall apart. If you don't have permeability, you cannot run reservoir simulation model, but you still can run this technology. Why? Because it's not based on equation. So you take all that data and you build a very simple static model. You use the static data, you use the dynamic data, the seismic and all that. The phase one that you spend a very, very large amount of time is that data preparation, data QC and QA. Then you build the comprehensive spatial temporal database. I'll talk about that in a minute. And then you build the TDM, and as I mentioned earlier, you have multiple neural networks that cascading one another. You history match that, and you validate it in time and space. If you can, then you have to go through that process until that is done. When it's done, then you can use it and deploy it for field development planning and implement it in the field, get the data, put it back into the comprehensive spatial temporal database, and that is a circle that can always be green and go. So the top-down model is the structure of it is usually determined by three factors. the main objective of the project, the size and the age of the field that being modeled, and the quality and the quantity of the data that you have. Another set of things that you have to use is a series of intelligent agents that's going to help you in order to make sure that many things that you are looking for are going to be used. So before, I have only very little time left. I cannot show you the use cases, but let me tell you a bit about this spatial temporal database. So let's imagine that this is a field, these are the wells that we have. The first thing we do, we build a Cartesian grid in that, and then we identify the outer boundary, and then we use Voronoi graph theory in order to identify polygons for each well. One of the things the fact that you do that, you cannot do that for all the wells at the same time, because in the real world, you can never, if you have 100 wells, those 100 wells were not drilled all at the same time. They were drilled probably in 10 different phases at 10 different times. So if this is the phase number 1, as you can see, the phase number 1, you only have 3 wells. And when you do the Voronoi polygons, you have these areas associated with them. Then in phase 2, now there was 3, now you have 4, 5, 6, and 7. What happens now, it changes the area that each well has the polygon. And when in the phase 3, when you go, again, changes. So that's step number 1. Step number 2 is we know that, this is the same example that you saw, that in the reservoir, offset wells impact each other a lot. So if you're taking the 2 offset wells for each well, during the phase 1, these 2 and 3 are offset of number 1. But once you go to the second phase, then the well number 4 become closer than well number 3. So instead of 2 and 3 now, to this particular well, number 2 and 4 become the offset wells. And later on, as you go to the next phase, then the same well has 4 and 8 as its 2 offset wells, if that's how many offset wells that you're looking at. So when you are building a spatial temporal database, even static information of W1 of well 1 or each well will change. If you go back and look at this, the average value of porosity, gamma ray, density, everything that you do for well number 1, it changes as a function of time. We call this dynamically modified static information. And these information are going to be used because they're going to impact the production and the injection as a function of time. And that's why we call it spatial temporal. Another thing that we have to say is that when you compare the TDM to the numerical reservoir simulation, the reservoir simulation modelers may think that we're building, or they can mention it, that we're building sector models, which is correct. You actually, for every well, all the wells that are around it and are contributing to it, to its production, impacting it. Every time you build a model, that's how it is, and then you bring them all together, and the final model is that. And this is what I was talking about, the intelligent agents. The physics and geology-based constraint boundary conditions, the reservoir management constraint, GOR or water cut, and every other, the surface facility issues that you have, all of these can be identified as intelligent agents that go and sit there and literally it's they look at the supervised learning and make sure so supervised learning goes beyond just the data, but also these intelligent agents and make sure things happens correctly. This is the formulation of the TDM, if you want to put it in a very simple. So it says that the production of the well I is a function of a subset of all of these parameters. And I show you what these parameters are. These parameters are dynamic characteristics of the well at time t, a dynamic of offset producer at time t minus 1, dynamic of offset injector at time t. This is static characterization for well. This is the static characterization of offset producer, static characteristics of offset injector, and then you have dwell-based and you have polygon-based. And this is static is a combination of both of them. And if you look at, if you could look at here, this is static information, dynamic information. This is the injector well, offset producer, offset injectors. This is the well itself at times t, but the producer at time t minus 1, injector at time t. I'm going to finish it here because it's almost 40 minutes. This is going to be my last model. The way we handle validation. Let's assume that we have a field that we're dealing from the year 2000 to 2029. That's what we want to do. So, and the fact is, in this particular well, we go from 20,000 to 2016, use all the measurement, and we build our history, and history match the model, and we actually have the data from till today, which is 2019 or end of 2019. Then we use those number of years, and we use them as blind history match. And then if that works, then we'll forecast it. So it's 40 minutes. I'm going to stop sharing my screen and unmute. I have just unmuted.
Your line is now unmuted.
So, any question, I'd be happy to look at it. I'm now looking at the chat to see if there is any question. In the prediction step, what input did you provide other than location? The only input we provide during prediction is choke setting. And sometimes when you have wellhead, and these two are good, choke setting and wellhead. Sometimes only wellhead, sometimes only choke setting, and some other times choke setting and wellhead. If you operated these wells different than the other wells used to train the model with the answer is yes. As long as the inputs are the same thing, for example, as long as the inputs are injectors, water injection, gas or CO2 injection, and different. Of course, it has to be in the same range, but when you do history matching on real-world field, you always have enough data in the range that can take care of that. Can you give some more detail in the SPM? Of course, I will be happy to do that, but it's very hard really to do that right now. So smart proxy, literally everything that I said about TDM applies to smart proxy as well. Difference is the data does not come from real world. The data comes from a numerical reservoir simulation. And the beauty of it is, with the smart proxy is you almost guaranteed you're going to succeed because you have the option of do whatever you want and generate any type of data that you would like to have. The next question is, have you tried some more complex neural network morphologies, the LSTM and CNN? The answer is absolutely yes. Actually, maybe the math of LSTM or RNN or CNN is different. I'll talk about that in a second. Maybe the math is more complex, but they are not really more complex. They're actually more simple than regular neural network. The reason for that being that LSTM and RNN, the recurrent neural network, and long short-term memory networks, these are purely time-dependent neural networks. If you go back and look at their history and why they were developed prior you using it yourself, you'll find out that they were really developed mainly to deal with with language, specifically LSTM. They wanted to build captioning for images, and they wanted to identify which part of the words should be used and which parts should not be used. That's why they call it long-term and short-term. The short terms are the data or the words that are used very closer to the next word that they're going to come up with. The long one are the oldest one. And then if you look at it, literally LSTM is like decline curve analysis in a little bit more complex fashion. And we did a lot of research using LSTM and TDM, and because you have to include the version of LSTM that they use, and the algorithms are available in many of these libraries, we found out that are not very good to do reservoir-related data. You can actually get very good results for a single well only. The space is completely gone, and you cannot do a lot of things that you have to do with those. I believe that we provide better time, space, resolution, standard network. LSTM does not, I'll guarantee you that. At least based on the research that we have done for a few years. I'm sure you can do your own research and come to your own conclusion, and I'll be happy to find out if I was incorrect. How do you decide important feature? The way you decide, and that's a very good question. How you decide the important feature? It has to do one of the key issues with AI and machine learning has to do the curse of dimensionality, the very large number of dimensions or parameters that you have and you want to deal with. The issue actually is that we use a fuzzy pattern recognition technology to identify which parameters to use. But this is one of the very key issues this is one of the key issues that's going to play a role. The next one is yes, but the recurrent CNN can handle spatial temporal. Okay, I'll be very interested to understand what is the recurrent CNN. If by CNN you mean convolutional neural network, convolutional neural network, when you go into the detail of it, it is a signal processing plus neural network that was done in order to do image recognition. And if you're doing image recognition, then it's a completely different story. You might be very successful with CNN. The key is that at least the way I approach reservoir engineering, I don't look at it as an image processing issue. It's a data processing issue. So when you do the choke setting optimization, how did you treat other variables? I'm not quite sure if I understand what that means when you choke setting. Okay, so when we do choke setting, since that is we just modify that and see and everything stays the same in order to find out how choke setting impacts the production. You update the static properties dynamically, or these properties are considered dynamic. No, they're not considered dynamic. They are porosity, permeability, gamma ray, density, V-shale. All of these items are static information. But when we're developing the spatial temporal database, it's not only the offset well that is impacting the production of the focal well. It is due to the range from where the offset well is to where the focal well is. That area has a certain amount of value of gamma ray of porosity, or the range, that polygon. And since polygon changes as a function of time, because the number of wells changes as a function of time, the number of wells that you produce, or a producer that you drill, or injectors that you drill, they will change the polygon. And although the static information for the well doesn't change, but since you're just using simple Kriging in order to generate the value for the polygon, that's what it modifies. I don't know if I understood and answered it correctly or not. You opted to say, okay. Did you say the inputs are just choke setting and wellhead pressure? Yes, that's what I said. How are the information like logs? Because the logs and well location, and of course well location is very, very important. That's not a that's something that you never change. If you drill a well, that stays there. So that information is always there. However, the logs and all of that stuff were used in order to build the model. So they have already impacted the pattern that has been generated by a complex set of neural networks that created the patterns that are there. But if for a particular well, as it happens something in the future, then all you have to do is to change the dynamic information, because those static information do not change unless you drill new wells and it changes the polygon's value. Did you take a median value for other variables, or did you optimize choke setting by each well? We optimize choke setting by each well. Do you lag your data sets so as to incorporate time? I don't know if I understand it, what you mean by that, because we use T-1 and T-2 sometimes for some of the parameters. Now, if by lagging you mean creating those 3D, that goes back to CNN and LSTM, which you have to create 3D data. Literally, you regenerate your data by moving them one time step or two time step, and you use them. And we have done that a lot. We came to conclusion that doesn't work well. That's why we stopped it. And that's our research. I'm sure others are doing the research. If they are successful, then we'll be very happy to learn from them. Okay, do you lag? Okay, next one is how did handle the risk with upscaling static model properties? How did handle the risk with upscaling static model properties? I'm not sure if I understand what that means. There are we don't upscale. The key for us that we don't do anything about is we use the measured data. Given that for spatial-temporal database that we generate, we have a Cartesian grid behind that, so we use a very simple interpolation, very, very simple kriging, without any interpretation. And we generate these data, gamma ray, porosity, all the static information for that. And we call it a static model. That static model literally takes 10 minutes to generate after you have the data. It's literally nothing. That's why it's not a good idea to even call it static or a geological model, because people who build geological model, they spend a very, very long amount of time to do that, and they spend a lot of interaction. We don't do that. That's why we don't really call it a static model. This is just to make sure that the static data that we have and the measurements are playing a role in space that help build the top-down model. I think I got all the questions that came through the chat. I think I believe that everybody is unmuted in order they need to have any question. There's 8 minutes left. How it would output geology? Well, the geology, the one I showed you, is because two of the outputs that we get are pressure, reservoir pressure, and water saturation. So when you get them for different locations at different times, then you can map them, and that's how you get the geology. And in what I showed you actually, when we presented that to that company, they told us that they're glad that we used their seismic input interpretation, which identified certain faults and certain high permeability places, and we told them we didn't. We did not use any of their interpretation. We just used actual data, and that is the pattern that came out of the process, and that's why how the geology works. So can you do transfer learning from one field to another? That's a very, very good question. That is something we're currently doing research on. I don't know the answer to that question. My answer is hopefully yes, but I don't know how. We are right now working on a project, and we're using that as a research topic. The transfer learning technology that's out there, it's not for engineering related process. The question is, how do you modify in order to... So another question that was earlier asked about convolutional neural network. What we do, we call it deconvolutional neural network, because literally, but what we've learned is from the convolutional neural network. One of the things we've learned is everything that people have been doing in Google and in Facebook and in other places, which is non-engineering related AI and machine learning algorithm, when you deeply
study them and understand what they do, one thing you find out you shouldn't be doing is applying it to engineering. But another thing you find out that you should be doing is to learn what was it that they were trying to solve, and what did that technology that they generated, transfer learning is a good example of that, or even convolutional neural network, what did they do in order to address the problem that they were trying to solve? And when you learn that, then it gives you some guidelines of how to use those ideas, not those algorithms, but those ideas to apply it to these type of approaches and solve the problems that you're looking for. And that is what we are trying to address when it comes to transfer learning. I don't have an answer to it, but it's a topic that we are currently doing research on. You mentioned kriging is used, but this requires sufficient data. That is true to model the variogram. That is true, but again, you cannot deal with anything other than the data that you have. So usually when you have 30, 40, in some cases hundreds of wells, those locations will help you to build the model. And even if it is not very, very correct, that's okay. As long as, because again, those things that are correct are the measured data. And you don't literally, or during remember I talked about curse of dimensionality. When you deal with the dimension, identifying which dimensions you want to use, then you can figure out whether those polygon those static parameters that was done for the polygon based on these kriging, if they don't work, your neural network is not going to use it. The next is, what is deconvolutional neural network? I'm writing an article on that. The deconvolutional neural network literally is the following. Because the word convolution means combining variables to one another, right? And what we're doing, if you look at the historical data, you never find a historical data to include a straight, look like a decline curve analysis that comes from the numerical reservoir simulators, right? It's always up and down, up and down, up and down. And those up and down, the data comes from not from the nature, but from human beings. The way we operate the wells, not from the permeability and porosity. So a deconvolutional neural network is a neural network that you provide all that complex data to it, but then when you drill in a new location, it gives you a very nice, without a lot of up and down, it looks like a very simple decline curve analysis well, something that you get from the numerical reservoir simulator. That kind of, I had actually something like that to show you, but the time didn't. So you're deconvolving the time and space. You're deconvolving, this neural network is deconvolving the change that porosity and permeability and static parameters have on the production, and the impact that choke setting and wellhead pressure and injection has on the parameter. That's why I call it deconvolutional. Can skin buildup versus time be taken into account? If you have that as an actual, because a lot of times skin is interpretation, has not as much to do with actual measurement. But if you do have it as an actual measurement and you want to use it, the answer is yes, you can take it into account and include it. I have another minute to go, actually. I think we're over.
I think so. I think we're a couple minutes past 3, but I did want to thank you, Shahab, for the very interesting and thought-provoking presentation and discussion and answering all those questions. Appreciate it. Appreciate the pleasure. All that. So, and thanks to everyone else, and hope everyone has a great weekend.
Have a great day, everybody.